Okay, so this is problem number 3 on our review. And again, these are all conservation of momentum. So in this case, we have two cars that collide. So it says at the intersection of Texas Avenue and the University Drive, a small subcompact car of mass 900 kilograms, so we're going to call that MA, traveling east on University collides with a maroon pickup truck of mass 1,500 kilograms that is traveling north. So here's our picture here. And remember, we always have to have a sign convention. So we're going to use our sign convention here that up and to the right is positive. So we're going to call east positive and we're going to call north positive. So then west and south would be negative because momentum, just like velocity, is a vector quantity and it has both magnitude and direction. The two vehicles stick together as a result of the collision, and immediately after the collision, the wreckage is sliding at 16 meters per second in the direction of 24 degrees east of north. So this is east of north. Okay, so this is the combined velocity. Calculate the speed of each vehicle just before the collision. Friction forces between the vehicles and the road can be neglected during the collision. So this is actually an easy problem if you do a momentum triangle. So a momentum triangle, you have to have a frame of reference. And as long as you know that vectors are added head to tail, it makes it very easy. So if I had my frame of reference, again, which is the y and the x, so I'm just going to draw a dotted line like this. This is my x, this is my y, just like in the picture. So after the collision, this is the combined mass, A plus B. Okay, so this is the total momentum after, which I'm going to call P prime. And remember, this is 24 degrees, just like the picture. So the total momentum before is equal to the total momentum after. So the momentum of car A before, remember it's going east, this is where I start. So I'm going to go like this. So this is going to be PA. From the head of this vector, I do the tail of the other. And this is PB. Okay. And this made it easy because they're perpendicular. So basically, I see that I have a right triangle. I can use my knowledge of math. If this is 24 degrees, this is 24 degrees, alternate interior angles. This is 66 degrees, and we see these are perpendicular, so it's a right triangle. So if I have a right triangle, and I know the hypotenuse, can I find the other two sides? Very easily. Okay. Now let's go back to the conservation of momentum before. So the total momentum after is the hypotenuse of the triangle, which I'm calling P prime. So what is P prime? Well, I know that P prime is equal to MA plus MB. That's the combined mass of the two vehicles, times V prime, which is the velocity after. So 900 kilograms plus 1,500 kilograms times the velocity after, which is 16. So if I do all that on my calculator, P prime comes out to be 38,400 kilogram meters per second. So that's the hypotenuse of my momentum triangle. Okay. So they asked me to find the velocity of both of them before. Okay. So I know that P is equal to MV. So if I want to find what these are, all I have to do is put that into P is equal to MV. Or I can just use this momentum triangle and say, okay, what is PA? So I know that PA is opposite the 24 degree angle. So I can say PA is equal to P sine of 34. And if I went too fast, remember, if I'm looking at a right triangle, I know sine of theta is opposite over hypotenuse. So if I'm using this, I could say sine of 24 is equal to the opposite PA over the hypotenuse, which is P prime. So if I move this to the other side, P prime, and I forgot the prime here. Whoops. Oh, I put the 34, it's 24. P prime times the sine of 24 degrees is equal to PA. So that's how I'm going to find the momentum of car A before collision, and then with the velocity, I'm just going to use the definition. So when I do that, I'm going to get 38,400 kilogram meters per second times the sine of 24 degrees, and this comes out to be 15,619 kilogram meter per second. Now, if I wanted to find the velocity, I would just use the definition of momentum and say P is equal to mv. Therefore, PA is ma times VA. And then I would rearrange that and say VA is equal to PA over MA. So it would be 15,619 kilogram meters per second divided by the mass, which is 900. Cancel my units. I end up with meters per second, which is the correct unit for velocity. So I see that VA is equal to 17.35 meters per second. Now, there's more than one way to do it. I could do the same thing for PB. I could use sine, I could use cosine, or I could use the Pythagorean theorem. It really, really doesn't matter. So maybe I'll say that PB is equal to I could do it the same way. I could say P prime times the sine of 66 degrees. Okay. So then I'll say 38,400 kilogram meters per second times the sine of 66 degrees, because PB is opposite the 66 degree angle. So that comes out to be 35,080 kilogram meter per second. And then again, I use my definition of momentum. P is equal to mv. So PB is equal to mb times VB. And rearrange that. So, and there's no prime here. So I end up with VB is equal to PB over MB. So 35,080 divided by 1,500, and that comes out to be 23.4. So what I do is I use the prime to represent after the collision. So the total momentum before is equal to the total momentum after. But vector momentum, like velocity, is a vector, so you cannot add them algebraically. You have to add them vectorially, which means adding them head to tail. And again, this is an example of a two-dimensional collision between cars.